Turn off the lights, my friend. I am HyperSleep Logs. Together, we're stepping into the deep mysteries of the cosmos. Our journey begins right now. Get comfortable. Pull your blanket up a little. Let your shoulders drop. Let your jaw relax. There's nowhere you need to be right now. Nothing you need to figure out. The day is done, and all I'm asking you to do for the next little while is just listen. Tonight, we're going to go on a journey together. A slow one. A quiet one. But one that might just be the most mind-expanding trip you've ever taken from the comfort of your own bed. We're going to ask one simple question. What if the moon disappeared tomorrow? Not faded. Not slowly drifted away. Just gone. Vanished. As if it had never been there at all. And I want you to really sit with that for a second. Picture it. You step outside tonight, maybe you're taking out the trash, or maybe you just want some air. You look up. And where that familiar glow used to be, that round, silver-white lantern that has hung in the sky for every single night of your life, there is nothing. Just a gap. A dark patch between the stars. A kind of absence that feels almost physical, like a missing tooth your tongue keeps finding. The moon is gone. So, what happens next? Take a slow breath. Settle in. Because I'm going to tell you everything. The very first thing you'd notice, before anything scientific, before any catastrophe, before the ocean does anything strange, is just the darkness. Real darkness. The kind of darkness that most people living in the modern world have genuinely never experienced. If you live in a city, or even a suburb, your nights are never truly dark. There's always a glow from somewhere. Streetlights, windows, the haze of light pollution bouncing off low clouds. And even when you're out in the countryside on a clear night, the moon, when it's full, is bright enough to cast shadows. Bright enough that you can read by it, if you hold a book close enough. Bright enough that hikers use it to navigate, that hunters have used it for thousands of years to move through the dark. The full moon reflects about 1/10 of 1% of the sunlight that hits it. That sounds tiny. And in absolute terms, it is tiny. But it's just enough. Just enough to turn darkness into something navigable. Just enough to make the night feel like a softer version of day, rather than a complete void. Without it, the night would become something different entirely. Imagine walking outside and looking up on a clear, moonless night. Without any light pollution. Without the moon. The Milky Way, our galaxy, seen edge on, would be so bright that it would cast a faint shadow. You'd see it as a river of light so dense and so luminous that it would look almost like a cloud. Stars that you've never seen before in your life would appear. Thousands of them. The sky would look fuller and stranger and more overwhelming than you could probably imagine right now. It would be beautiful, honestly. And terrifying. In equal measure. Animals that rely on moonlight to navigate, sea turtles that use the reflection of the moon off the ocean's surface to find the water after hatching, moths that use the moon as a compass, some species of dung beetles that actually use the Milky Way to roll in a straight line, would be thrown into confusion. The night ecosystem, which we often forget about entirely, would begin to shift almost immediately. But the darkness is just the beginning. The darkness is the gentle part of this story. Within hours, not days, not weeks, but hours, the ocean would start to behave differently. Here's something worth understanding. The moon is the primary driver of Earth's tides. It's responsible for roughly 70% of the tidal forces that move the ocean. The sun contributes the other 30%. Together, they create the rhythmic rise and fall of sea level that we call the tides. Twice a day, in most places, the ocean rises, reaches its peak, and then falls back again. The reason the moon can do this, from nearly 250,000 miles away, is gravity. Gravity doesn't just pull. It pulls more strongly on the side of Earth closest to the moon than it does on the far side. This difference in gravitational pull across the diameter of Earth creates what scientists call a tidal force. On the side of Earth facing the moon, ocean water gets pulled toward the moon, creating a bulge of raised water. On the opposite side of Earth, the ocean water is being pulled less strongly than the solid Earth itself, so it effectively gets left behind, creating another bulge on the far side. These two bulges are the high tides. As Earth rotates beneath them, different coastlines move through the bulges and experience high and low tides roughly twice per day. The moment the moon disappears, those tidal bulges are suddenly without their cause. The gravitational architect has left the building. The water that had been pulled and shaped into those bulges has nowhere to go but outward, spreading chaotically as it seeks a new equilibrium. There would likely be a period of large, disorganized waves along many coastlines, not the focused devastation of a tsunami, but a broader, more confused surging as the ocean redistributes itself. And then the new reality would settle in. Tides driven only by the sun would still exist. The sun is not small, gravitationally speaking. But solar tides alone would be about 1/3 the strength of what we have now. The difference between high tide and low tide, which in some places, like the Bay of Fundy in eastern Canada, can be as dramatic as 50 feet, would shrink significantly. Most coastlines would see tidal ranges of just a foot or two, maybe less. For a moment, this might sound like good news. Smaller tides, calmer coasts. But the consequences of this change ripple outward in ways that are difficult to fully grasp. Let me take you to a rocky shore. Not a beach with sand and umbrella chairs and sunscreen. I mean a real rocky coastline. The kind with barnacle-covered boulders and tide pools full of tiny creatures. The kind where the smell of salt and seaweed hits you before you even see the water. The kind where, if you come back in 6 hours, half the rocks that were underwater are now exposed to the air, and the ones that were dry are now submerged. This is what scientists call the intertidal zone. And it is one of the most extraordinarily productive and biologically diverse ecosystems on the entire planet. Everything that lives in the intertidal zone lives there because of the tides. The barnacles that cement themselves to rocks and filter food from the water when the tide comes in. The mussels that cluster in thick blue-black masses in the mid-tide zone, staying moist enough to survive exposure and submerged enough to feed. The sea stars, starfish, that prowl the lower intertidal zone hunting mussels and urchins and snails. The hermit crabs picking their way through puddles. The limpets scraping algae off rock surfaces. The tiny fish called sculpins that hide in the crevices and dart through tide pools like living shadows. Each of these species evolved in a world where the tide goes in, and then the tide goes out. Where the water level changes twice a day. Where there is a reliable, predictable rhythm to wet and dry, exposed and submerged. With the moon gone, that rhythm collapses. The intertidal zone as we know it would shrink dramatically. The wide bands of habitat that stretch between the highest high tide and the lowest low tide would narrow to a fraction of their former width. Species that evolved for a certain tidal range would find their world constricted. The ones higher up the shore, adapted to long periods of exposure, would be stuck underwater more of the time. The ones lower down, adapted to brief exposures, would barely see air at all. The delicate zonation that makes intertidal communities so diverse and so productive would blur and compress. Many species would not adapt in time. They would decline. Some would go locally extinct. And because intertidal species form the foundation of larger food webs, shorebirds eat intertidal invertebrates, otters eat sea urchins, seals rest on tidal rocks and hunt in tidal waters, the effects would cascade upward through the food chain. There's another kind of coastal ecosystem that depends on tides even more critically than rocky shores. Estuaries. An estuary is where a river meets the ocean. It's a place of mixing, fresh water flowing down from the land, salt water pushing in from the sea, and in between them, a brackish gradient where the chemistry changes from one bank to the next, from the surface to the bottom, from high tide to low tide. Estuaries are sometimes called the nurseries of the sea. This is not a metaphor. It is almost literally true. An enormous percentage of the fish and shellfish species that adults live in the open ocean actually begin their lives in estuaries. They hatch there. They grow there. They hide from predators in the marsh grass and mangrove roots. They find their first meals in the nutrient-rich, sheltered waters where fresh and salt water mingle. Salmon, striped bass, flounder, shrimp, blue crab, oysters. The list goes on and on. Species that support billion-dollar fishing industries, species that feed coastal communities around the world, species that form the backbone of coastal food webs, they are all, in one way or another, dependent on estuaries. And estuaries are dependent on tides. Tidal flow is what drives the circulation in estuaries. When the tide comes in, it pushes salt water up the river channel, mixing it with fresh water and distributing nutrients. When the tide goes out, it carries water, and the young larvae and tiny organisms in that water back out toward the sea. Without strong tides, this circulation slows. Water stratifies. The heavier salt water sinks to the bottom and stays there. The lighter fresh water floats on top. The mixing that keeps estuaries oxygenated and productive stops happening. What you get instead is hypoxia. Oxygen depletion. Dead zones. We've seen this happen in places where human pollution has contributed to algae blooms and oxygen depletion, places like the Gulf of Mexico, where a massive dead zone forms every summer near the mouth of the Mississippi River. Fish and shrimp flee these areas or suffocate. The bottom becomes nearly lifeless. Imagine something similar, but permanent, and spreading to nearly every major estuary on Earth. The fishing industries of coastal nations would begin to collapse within years. There is something that coral reefs do that is, honestly, one of the most remarkable things in all of nature. Once a year, usually in late spring, on a night that follows the full moon, the corals of Australia's Great Barrier Reef all spawn at once. Not one species. Not one section of the reef. The entire reef. Hundreds of species of coral, simultaneously releasing eggs and sperm bundles into the water in a blizzard of pink and white that turns the ocean milky. Scientists who have witnessed it describe it as one of the most astonishing natural events on Earth. Seen from above, the reef looks like it's snowing upward. This event, called the mass spawning, has to be synchronized. A single coral polyp releasing its gametes alone in the dark ocean has almost no chance of successful fertilization. The eggs and sperm need to meet in the water, and for that to happen, every coral in the area needs to release its gametes at roughly the same time. The synchronization has to be nearly perfect. So how does the coral do it? How does a creature with no brain, no eyes, no nervous system as we would recognize it, a creature that is essentially a small, soft tube attached to a calcium carbonate skeleton, know exactly when to spawn? The moon. Specifically, the change in light levels as the moon moves through its phases. Corals are sensitive to light in extraordinarily subtle ways. They can detect the difference between full moonlight and new moon darkness. They can track the slow brightening and dimming of the moon over the 29.5-day lunar cycle. And it's this light signal, filtered through the water, that triggers the chemical cascade inside each coral polyp that eventually leads to the mass release of gametes. Without the moon, there is no lunar cycle. There is no light signal. There is no synchronizer. Coral spawning would not just be disrupted, it would be decoupled from any shared environmental cue. Some corals might still spawn based on temperature or other factors. But the beautiful, chaotic, seemingly miraculous synchrony of the mass spawning would be gone. Individual corals would release gametes at random times. Fertilization rates would drop towards zero. A generation of coral larvae would fail to form. Coral reefs support roughly 25% of all marine species. They cover less than 1% of the ocean floor. They are the rainforests of the sea, tiny in area, staggering in biodiversity and ecological importance. Their collapse would send shockwaves through marine ecosystems that would be felt for centuries. It's not just corals. The lunar cycle is threaded through the biology of a remarkable number of animals. It's as if life on Earth evolved a clock, and that clock runs on moonlight. The grunion. This small silver fish that lives along the Southern California coast comes ashore to spawn on the nights after a full or new moon during spring and summer. And I mean comes ashore literally. Female grunion ride breaking waves onto the beach, dig into the sand with their tails, and deposit their eggs, while males fertilize them right there on the beach. Then the waves carry the fish back to sea. The eggs develop buried in the sand, and exactly 2 weeks later, on the next high tide series, the hatchlings emerge and are swept into the ocean. The timing is calibrated to the tidal calendar almost perfectly. Without the moon, there is no reliable tidal calendar for the grunion. The spawning behavior, shaped by millions of years of evolution, would suddenly have no environmental anchor. The pololo worm. In the South Pacific, around Samoa and Fiji, there is a marine worm that lives in coral reef crevices and does something extraordinary once a year. In the last quarter of the moon in October or November, the worm's tail, packed with eggs and sperm, detaches from its body and rises to the ocean's surface. Millions of these reproductive tail segments fill the water in a brief, spectacular explosion of life. Local communities have harvested the pololo worm for centuries, knowing exactly when it will rise. The timing is so consistent that it's essentially a natural calendar event. Without the moon's phase cycle, the pololo worm's spawning signal disappears. The dung beetle. You might not think of a dung beetle as an animal with a relationship to the moon. But certain species of dung beetles navigate by the Milky Way on moonless nights, and by the moon when it's present. They roll their dung balls in straight lines by using celestial light as a compass, and the moon, when visible, is their primary reference. Take away the moon, and the night navigators of the insect world lose their brightest landmark. Sea turtles. Baby sea turtles hatching on a beach at night navigate toward the ocean by moving toward the brightest horizon, which, in a natural setting, is the ocean reflecting the sky. The moon contributes enormously to this reflection on calm nights. Remove the moon, and hatchlings on dark nights become more disoriented, more vulnerable to moving inland instead of toward the water. The list goes on. Certain species of fish, certain crustaceans, seabirds that use the moon to navigate on migration. Even some land animals, lions have been documented hunting more during the dark nights following a full moon, because in the period just after the full moon, nights are darker in the first half of the night, when lions most often hunt. Remove the moon, and behavior patterns shaped across millions of years of evolution suddenly have no environmental cue to attach to. Now I want to talk about something that plays out not over days or years but over millions of years. Because the most profound consequence of losing the moon is not what happens in the first hours or the first years. It's what happens to the orientation of Earth itself. Earth is tilted. Right now, the axis around which Earth spins, the invisible line that runs from the North Pole to the South Pole, is not straight up and down relative to Earth's orbit around the Sun. It's tilted at an angle of about 23.4 degrees. This is the reason we have seasons. In summer in the Northern Hemisphere is tilted toward the Sun, receiving more direct sunlight for longer days. In winter, it tilts away, receiving less sunlight at a lower angle for shorter days. If Earth's axis were perfectly upright, 0 degrees of tilt, there would be no seasons at all. Every day of the year, every location on Earth would receive the same amount of sunlight. The tropics would be warm and the poles would be cold, but there would be no summer, no winter, no spring, no fall. Just an eternal, unchanging sameness. If Earth's axis were tilted at a very steep angle, say, 80 degrees, one hemisphere would be essentially pointing straight at the Sun for half the year, and pointing almost directly away from it for the other half. The seasons would be extreme beyond imagining. The poles would experience months of continuous full sunlight followed by months of total darkness. The weather patterns would be so violent and so variable that stable ecosystems of the kind we know today could not exist. Earth's current 23.4 degree tilt is a kind of Goldilocks tilt. It gives us meaningful seasons that drive nutrient cycling, that trigger animal migrations and plant growth cycles, that create the climatic diversity that allows such an enormous variety of ecosystems to exist. But it's not so extreme that any single season becomes lethal for large swaths of the planet. This tilt is relatively stable. It drifts very slightly over long timescales. A cycle called the obliquity cycle takes about 41,000 years to complete, and during that cycle, Earth's tilt varies between about 22.1 degrees and 24.5 degrees. A small range. Stable enough that ecosystems can adapt to it without crisis. The reason Earth's tilt is so stable. The Moon. The Moon acts as a gravitational stabilizer. Jupiter and Saturn, the two massive outer planets, are constantly tugging on Earth's axis with their gravity. Over long timescales, without a counterweight, these tugs would accumulate and drive Earth's axial tilt into chaotic territory. The Moon's gravitational influence essentially damps out this wobble. It provides a stabilizing force that keeps the tilt within that narrow, comfortable range. Without the moon, computer simulations, run by astrophysicists who model the dynamics of planetary systems, suggest that Earth's axial tilt could wander dramatically over timescales of millions of years. The tilt could potentially range anywhere from near zero to as high as 85 degrees. The wandering wouldn't be fast, it would play out over tens of millions of years. But it would be essentially irreversible without something to arrest it. Earth's climate system, its ecosystems, its ocean circulation patterns, all of them are built on the foundation of relatively stable seasons. If the axial tilt begins to wander, every other aspect of Earth's environment eventually changes too. Let me describe for you what Earth might look like if the axial tilt reached its extreme. Imagine Earth tilted to 80 degrees. At the North and South Poles, regions that today experience 6 months of daylight and 6 months of darkness, respectively, with cold but survivable temperatures, the experience would become nearly incomprehensible. For half the year, the pole would be aimed almost directly at the sun. For 6 months straight, the sun would shine down relentlessly. Temperatures would not just get warm, they would soar. The ice caps would melt completely during this period. The meltwater would flood coastal regions globally as sea levels rose. And then the pole would swing away from the sun for the other 6 months. And the water that melted would freeze again. 6 months of brutal, total darkness, with temperatures plunging to levels colder than anything on Earth today. The climate swings would be so violent, so rapid on a geological timescale, that the kind of slow, gradual evolutionary adaptation that has shaped life on Earth over billions of years would struggle to keep pace. Meanwhile, the tropics, which today experience relatively mild seasonality because they remain close to the equatorial plane, would, in a high-tilt world, swing through enormous arcs of heating and cooling. The equatorial regions might experience some of the most extreme seasonality on the planet, baking under direct sunlight for months and then plunging into relative darkness and cold. The ocean circulation systems that today distribute heat around the globe, the Gulf Stream, the Antarctic Circumpolar Current, the deep thermohaline circulation that drives ocean mixing over thousands of years, would be disrupted by these extreme temperature swings in ways that are difficult to even model accurately. Ice ages of unusual severity would alternate with periods of global warming far beyond anything in Earth's current history. Life would likely persist. Life is remarkably resilient. But the life that survived would look nothing like what exists today. The great diversity of complex ecosystems, rainforests, coral reefs, temperate forests, grasslands, polar ecosystems, requires a degree of climatic stability to develop and persist over the long timescales that complex communities take to evolve. Remove that stability, and you remove the scaffold on which biodiversity is built. Before we go any further into what the world would become without the moon, I think it's worth pausing and really understanding what the moon actually is. Because the story of how the moon came to exist is extraordinary. It reads less like a piece of astronomy and more like an origin myth. We have to go back, far back, to a time about 4.5 billion years ago. The solar system was young. It was chaotic. The sun had only recently ignited, and around it, the planets were still forming from the spinning disk of gas and dust that had given birth to the solar system. Earth existed, but it was nothing like the planet you're lying on right now. It was molten, volcanic, bombarded constantly by the rocky debris of the still-forming solar system. The atmosphere, if you could call it that, was thick with steam and toxic gases. In this chaotic early solar system, there was another planet-sized body. Scientists call it Theia. Theia was roughly the size of Mars, about half the diameter of Earth, but substantial. A real planet. It had its own iron core, its own rocky mantle. It had been forming for tens of millions of years. And it was on a collision course with Earth. The collision, when it happened, is almost impossible to fully picture. Theia did not strike Earth head-on. Current models suggest it was more of a glancing blow, a sideways impact. But even a glancing blow at planetary scales is catastrophic beyond human comprehension. The energy released in the impact was enormous enough to partially vaporize both bodies. The outer layers of Earth and Theia, the mantles, the crusts, were blasted into orbit as an incandescent cloud of rock vapor and molten debris. The iron cores of both planets, however, were dense enough that they survived the impact relatively intact and merged together into what became Earth's new, larger iron core. The debris cloud in orbit was enormous. It stretched out around Earth like a chaotic, glowing ring of molten rock and superheated vapor. Over thousands of years, cosmically speaking, a very short time, this debris coalesced. Gravity pulled it together. Droplets of cooling rock merged and merged and merged until they formed a single body. The Moon. The early Moon was incredibly close. Perhaps only 25,000 kilometers away, compared to the current average distance of about 384,000 kilometers. At that distance, the Moon would have appeared enormous in the sky, perhaps 15 or 20 times larger in apparent diameter than it does today. The tidal forces on the young Earth would have been staggering. Tides hundreds of meters high. An Earth rotating so fast, a day lasting only 5 or 6 hours, that the tidal friction was immense. Over billions of years, tidal friction has gradually slowed Earth's rotation, lengthening our day from that early 5 or 6 hours to the 24 hours we have now, and simultaneously pushed the Moon farther away. The Moon is still receding. Every year, it drifts about 3.8 centimeters farther from Earth. Slowly. Steadily. Like a ship moving away from a shore. We know all of this, the giant impact, the shared origin of Earth and Moon, because of rocks. When the Apollo astronauts landed on the Moon between 1969 and 1972, they brought back samples. Boxes and bags of lunar rocks, carefully collected from different sites across the lunar surface. These samples came back to Earth and were analyzed by geochemists and planetary scientists, and what they found was extraordinary. The Moon rocks are almost isotopically identical to Earth rocks. Let me explain why that matters. Every planetary body in the solar system has a slightly different isotopic fingerprint, a slightly different ratio of different isotopes of elements like oxygen and tungsten and titanium. These differences reflect where in the solar disk the material that formed each planet originated. Mars has a distinct isotopic fingerprint. The asteroid belt has its own signature. Earth has its own. If the Moon had formed somewhere else in the solar system and been captured by Earth's gravity, which was one early hypothesis, its rocks should have a different isotopic fingerprint from Earth's rocks. They should look chemically different. They don't. The Moon's rocks have essentially the same oxygen isotopic composition as Earth's rocks. The same tungsten isotope ratios. The same titanium fingerprint. This is only possible if the Moon is made largely of the same material as Earth itself, material that was part of Earth before the impact, blasted into orbit by the collision. The giant impact hypothesis is not just a story. It is one of the best supported theories in all of planetary science. And it tells us something profound. The moon is not a stranger visiting Earth's sky. It is, in a very real sense, a piece of Earth. A fragment of our own planet, separated by violence and remade by gravity into a new world, orbiting at a distance that has been slowly increasing for 4.5 billion years. Here's something you might not have thought about before. The 24-hour day, the rhythm around which human civilization is organized, the clock that tells you when to sleep and when to wake, is a direct consequence of the moon. Not entirely, of course. Earth was always going to rotate. That rotation comes from the angular momentum of the material that formed Earth in the early solar system. But the speed of that rotation has been shaped, over billions of years, by the moon. In the very early days, Earth rotated much faster. A day was only 5 or 6 hours long. The moon, still very close, created enormous tidal bulges in Earth's solid rock. Yes, the rock itself deformed slightly under tidal forces, not just the ocean, and the friction generated by these tidal bulges gradually slowed Earth's spin. It's a slow process. But over 4.5 billion years, it has been extraordinarily effective. Earth's day has lengthened from 5 or 6 hours to 24 hours, and the moon has moved outward as a consequence. The angular momentum transferred from Earth's spin to the moon's orbit, pushing it farther away. This process is still happening today. Earth's rotation is still slowing, very slightly. Every century, the length of the day increases by about 1.4 milliseconds. This doesn't sound like much. And in human terms, it is barely detectable. But over geological time, it adds up. Without the moon, this tidal breaking would never have occurred. Earth would still be spinning very fast. A day on Earth would be a matter of hours, not 24 hours. The consequences of that rapid rotation would be significant. Stronger Coriolis forces shaping weather and ocean currents differently, a more flattened planetary shape, more violent atmospheric circulation. The Earth we would have, without the moon's billions of years of tidal breaking, would be measurably different in its daily experience for anything living on its surface. Some scientists believe, and this is a genuine scientific hypothesis, not just poetic speculation, that the moon may have played a role in the very origin of life on Earth. This idea is connected to the tidal pools hypothesis. Life on Earth began somewhere between 3.5 and 4 billion years ago. We know this from fossils, specifically, ancient structures called stromatolites that were built by communities of microorganisms, and which have been found in ancient rocks that old. But the question of where life began, the specific environment in which the first self-replicating molecules formed, is still actively debated. One leading hypothesis is that life began in shallow pools. Pools that were alternately wet and dry, filled by ocean water at high tide and then exposed to the air and sunlight at low tide. This wet-dry cycling is important because it concentrates chemicals. When water evaporates from a pool, everything dissolved in that water, amino acids, nucleotides, mineral ions, gets concentrated into a smaller and smaller volume. The molecules are forced into close proximity. Chemical reactions that might be too slow or too dilute to happen efficiently in the open ocean can happen rapidly in a concentrating tide pool. Experiments in the laboratory have shown that this kind of wet-dry cycling can promote the formation and elongation of simple RNA-like molecules, molecules that might be precursors to the first self-replicating genetic material that is the foundation of all life. The stronger the tides, the more dramatic the wet-dry cycling. The earlier moon, much closer to Earth than it is today, would have created extraordinarily powerful tides. Tidal zones would have been broad, dramatic, and subject to extreme cycling. The conditions for concentrating and experimenting with prebiotic chemistry would have been ideal. If this hypothesis is correct, and it remains a hypothesis, not a certainty, then the moon was not just a stabilizer of the conditions that allowed life to persist and diversify. It may have been part of the mechanism by which life began in the first place. Take that in for a moment. The moon, hanging in the sky tonight, may be part of the reason that you exist at all. For as long as humans have existed, the moon has been there. Every human who has ever lived has looked up at it. Every culture in the history of civilization has given it a name, a story, a meaning. The moon has been a god, a goddess, a rabbit, a face, a lantern, a mirror, a clock. It has been the subject of myths and rituals and art and science since before the written word existed. The word month comes from the word moon. In almost every language on Earth, the unit of time we call a month has its roots in the lunar cycle, the roughly 29.5 days it takes the moon to go from one new moon to the next. Our earliest calendars were lunar calendars, tracking the cycle of the moon to organize agricultural work, religious observance, seasonal preparation. The Islamic calendar is still a purely lunar calendar. The Hebrew calendar and the Hindu calendar are lunisolar, blending the lunar cycle with the solar year. The moon told our ancestors when to plant and when to harvest. When the moon was full, they could work and travel at night, a huge practical advantage in a world without artificial light. When the moon was dark, the nights were dangerous and navigation was harder. The entire rhythm of life for most of human history was shaped around the availability of moonlight. Farmers in many traditions planted root vegetables during the waning moon, when the moon's gravitational pull was supposedly drawing water downward, and leafy vegetables during the waxing moon, when water was supposedly drawn upward. Whether the moon's gravity actually affects soil moisture and plant growth in a meaningful way is scientifically debated, but the practice reflects how deeply the lunar cycle was embedded in daily agricultural life. The moon governed seafaring. Sailors used the moon not just for light at night but for navigation. The ability to calculate longitude at sea, one of the great navigational challenges of the age of exploration, was eventually solved in part through lunar distance calculations, using the moon's position among the stars as a kind of clock. Stories about the moon are woven into every culture. The Japanese tell of a moon rabbit pounding mochi. In Norse mythology, two children, Juki and Bill, were taken up to become the moon. Native American traditions have rich stories of the moon as a living presence who watches over the night. Greek mythology gave us Selene, the moon goddess who drove her silver chariot across the sky. Chinese mythology tells of Chana, the moon goddess who lives in a palace on the moon with a jade rabbit for company. These stories are not just charming. They tell us something real about what the moon has meant to human beings across all of history, a constant companion, a reliable presence, a source of light and order in the darkness. Something so consistent and so ancient that it became, in culture after culture, the symbol of cycles, of femininity, of time, of mystery, of the reliable return of light after darkness. And all of that accumulated human meaning, all of that mythology and poetry and art and science, is built on the foundation of a physical object. A real world, orbiting at a real distance, made of real rock. The moon that we see from Earth, that smooth-looking silver disk or crescent, looks very different up close. The surface of the moon is ancient. It has been geologically dead for roughly 3 billion years. There are no active volcanoes. No tectonic plates shifting and refreshing the crust. No liquid water reshaping the landscape. No wind, no weather, no erosion of any kind. The only thing that changes on the lunar surface today is the slow, relentless bombardment by meteorites and the gentler rain of micrometeorite dust and charged particles from the solar wind. Because of this geologic stillness, the moon preserves its history in a way that Earth cannot. Earth's surface is constantly being renewed by plate tectonics and erosion. The oldest rocks on Earth's surface are about 4 billion years old, and they're rare. The moon has rocks of similar age all over its surface, because there's nothing to erase them. The dark patches you can see on the moon with the naked eye, the regions that the early astronomers called the Maria, the Latin word for seas, because they thought they might actually be bodies of water, are ancient lava plains. Between 3 and 4 billion years ago, the young moon was volcanically active. Magma welled up from the interior and flooded the large impact basins, creating the flat, dark plains we see today. Since then, they've been bombarded by meteorites, covered in a fine layer of dust called regolith, and left essentially unchanged. The bright regions, the highlands, are the original lunar crust, formed when the moon first solidified from the molten state that followed the giant impact. They are heavily cratered. Every crater tells the story of an impact, some ancient, from the period of heavy bombardment early in the solar system's history, some more recent. The largest craters are hundreds of kilometers across. Some have been partially flooded by later volcanic activity. Some have central peaks, formed when the rock beneath the impact site rebounded upward after the initial collision, like a slow-motion splash of water frozen in stone. The surface is covered in regolith, a blanket of fine, powdery material formed by billions of years of meteorite impacts grinding the lunar rocks into dust. This regolith is sharp and abrasive at the microscopic level, because there's no wind or water to round off the edges of the tiny fragments. The Apollo astronauts found it clung to everything and was surprisingly difficult to deal with. It got into their suits, their equipment, their spacecraft. At the poles, in permanently shadowed craters where sunlight never reaches, there is water ice. Ancient ice, deposited over billions of years by comets and asteroids. This discovery, confirmed in recent decades by lunar orbiting spacecraft, is one of the most significant findings about the moon in the post-Apollo era. That ice is a resource. In a future where humans might establish a sustained presence on the moon, that ice is invaluable: water for drinking, water for growing food, water that can be split into hydrogen and oxygen for rocket fuel. On July 20th, 1969, a human being stood on the moon. Neil Armstrong descended the ladder of the lunar module Eagle, a spindly, ungainly spacecraft that looked nothing like the sleek rockets of science fiction, and placed his boot on the lunar surface. The gray dust, compacted by that first step, held the impression of his boot print. It still holds it today. There's no wind on the moon. No rain. Nothing to erase it. The words he spoke as he took that first step have been replayed so many times that they risk losing their power. But if you strip away the familiarity and try to really understand the moment, a human being, having traveled through the vacuum of space for 3 days, standing on a world 250,000 miles from everyone and everything they had ever known, it is a genuinely staggering moment in the history of life on Earth. Buzz Aldrin, who followed Armstrong onto the surface, described the landscape as magnificent desolation. Two words that capture it perfectly. The beauty of the stark, ancient, cratered surface. And the absolute, total, profound absence of anything living. The Apollo program sent 12 human beings to walk on the moon between 1969 and 1972. They collected about 842 pounds of lunar rock and soil, samples that are still being studied today, still yielding new insights about the early solar system. They planted flags that are still standing, though the ultraviolet radiation from the sun has almost certainly bleached the colors from them long ago, leaving them ghostly white. They left scientific instruments that ran for years after the astronauts came home. And then, for reasons that are still a source of some frustration and puzzlement, humanity stopped going. 50 years later, we have not returned. The footprints of 12 men remain the only direct human contact with any world beyond our own. The equipment left behind sits silent on the gray plains of the moon, slowly being covered by the finest layer of dust. The laser reflectors that the Apollo astronauts placed on the surface, precisely engineered arrays of corner prisms designed to bounce laser beams back to Earth, are still used today to measure the distance to the moon with extraordinary precision. That's how we know it's moving away at 3.8 centimeters per year. In the years ahead, new lunar programs, from NASA, from private companies, from China, from other nations, are aiming to return humans to the moon. To stay, this time. To build. To use those polar ice deposits. To establish a foothold on that ancient, familiar, extraordinarily important world that has been orbiting Earth for 4.5 billion years. The moon is not going to disappear tomorrow, or next year, or in 1,000,000 years. But the moon does have a future, and that future is worth knowing about. As we discussed, the moon is slowly moving away from Earth, about 3.8 centimeters per year. This is an immeasurably slow recession in human terms. In a human lifetime, the moon gets perhaps 2 or 3 meters farther away. That change is completely imperceptible. The moon looks exactly the same size to your eyes as it did to the eyes of every human who has ever lived. But over geological time, the change accumulates. 500 million years from now, the moon will be noticeably farther away. The tidal forces will be weaker. And one of the most remarkable coincidences in our current solar system, the fact that the moon and the sun appear almost exactly the same size in Earth's sky, making total solar eclipses possible, will be gone. The moon will appear smaller than the sun, and total solar eclipses will become impossible. Annular eclipses, where the moon is too small to fully cover the sun, leaving a ring of fire around its edges, will be all that's possible. This means that total solar eclipses, one of the most spectacular natural phenomena on Earth, are something unique to this particular moment in the solar system's history. We happen to live at the one time in Earth's history when the size and distance of the moon conspire to create this perfect covering of the sun. Dinosaurs did not see total solar eclipses quite like ours. Humans alive a few 100 million years from now will not see them either. We are cosmically lucky. On even longer timescales, billions of years from now, as the sun evolves toward the end of its life and expands into a red giant, the entire inner solar system will be radically altered. The details are complex and uncertain. But the trajectory of the moon and Earth is, on these timescales, part of a larger story of the evolution of the sun itself. Long before any of that, however, something else will happen. Eventually, tidal braking will slow Earth's rotation until Earth and Moon are tidally locked to each other, with Earth showing the same face to the Moon as the Moon already shows to Earth. At that point, the moon will no longer be receding. The tidal energy transfer will stop. The two worlds will orbit each other, face to face, frozen in a gravitational embrace. How long until that happens? Estimates suggest something like 50 billion years, which is about 3.5 times the current age of the universe. It will never happen, practically speaking, because the sun will have long since ended its life on the main sequence and taken the inner solar system with it. So the moon will continue to accompany Earth for as long as Earth and the moon exist, slowly drifting outward, gradually weakening in its tidal influence, but never leaving. It's worth looking at what other planets in our solar system tell us about what Earth might be like without the moon. Mars is an interesting case. Mars has two moons, Phobos and Deimos, but they are tiny. Phobos is about 22 kilometers across. Deimos is even smaller. These are not moons in the sense that Earth's moon is a moon. They are captured asteroids, tiny rocky bodies with essentially no tidal influence on Mars. Mars also has an axial tilt, currently about 25.2 degrees, similar to Earth's. But Mars has no large moon to stabilize its tilt. And the geological and climate record of Mars tells a story of enormous axial variability over Mars's history. Mars's axial tilt has ranged from near zero to perhaps as high as 60 degrees or more over the past few billion years. The Martian poles bear geological evidence of dramatic climate swings, layered deposits of ice and dust that reflect periods of very different obliquity. The Mars that exists today, cold, dry, thin atmosphered, may be very different from the Mars that existed 1 billion or 2 billion years ago, in part because of its unstable axial tilt. The connection between that instability and the current barrenness of Mars is debated among scientists, but it is a real consideration. Venus, by contrast, has no moon at all. And Venus has an axial tilt of almost 177 degrees, which is essentially saying that Venus is nearly completely inverted relative to its orbit. It rotates backwards compared to most planets, and very slowly. A day on Venus is longer than a year on Venus. The climate of Venus, scorching hot, with a surface temperature of nearly 465 degrees Celsius and an atmospheric pressure 90 times that of Earth's, is extreme in ways that are only partially related to its lack of a moon, but the absence of any stabilizing influence is part of the broader picture of why Venus evolved so differently from Earth despite being roughly similar in size and composition. Earth, with its large moon, has been uniquely fortunate. Not just in having a moon at all, but in having a moon of this particular size, at this particular distance. A moon that formed in a particular way, out of Earth's own material, and ended up being exactly the right size to create those beautiful total solar eclipses, to drive those productive tides, and to stabilize that crucial axial tilt. I want to bring you back from the deep past and the distant future. Back from the volcanic young Earth and the chaos of the giant impact. Back from the dead zones and the wandering tilt and the bleached Apollo flags and the dark polar craters where ice has waited for billions of years in a permanent shadow. Back to right now. Tonight. Wherever you are. You're warm. You're comfortable. The day is done. And somewhere above you, through the ceiling, through the clouds if there are any, through the atmosphere, the moon is out there. Maybe you can see it through a window. Maybe it's full right now, lighting up the night. Maybe it's a slim crescent. Maybe it's new and you can't see it at all. But it's there. 384,000 kilometers away, give or take, a world the size of about 1/4 the diameter of Earth is traveling through space alongside us. It has been doing this for longer than any living thing has existed. It was there before the first bacterium. It was there before the first animal. It was there before the first tree. It was there before the first human looked up and wondered what it was. It stabilizes the ground under your feet, in the sense that it stabilizes the tilt of the axis that gives us our seasons and our climate stability. It moves the ocean, in that slow rhythm of rise and fall that has shaped coastlines and ecosystems for hundreds of millions of years. It lit the nights of every human ancestor going back to the very beginning, and it carries in its rocks the chemical fingerprint of a collision that happened before the Earth as we know it even fully existed. It is not just a light in the sky. It is a partner. An ancient, silent, gravitational partner. And the fact that it is there, that of all the ways the early solar system could have arranged itself, it arranged itself in a way that left us with this particular moon at this particular distance, is one of the great pieces of luck in the long story of life on Earth. Let's go back, one more time, to the darkness. Imagine the night sky without the moon. Not as a terrifying thought, now. Just as an image. A clear night. No city lights. No clouds. And no moon. The sky above you would be so full of stars it would almost feel overwhelming. You've heard the phrase, you can't see the forest for the trees. In a moonlit sky, the moon is so bright that it obscures the forest of stars behind it. Remove it, and the forest appears. You would see the Milky Way, our galaxy, as a river of light cutting across the sky from horizon to horizon. You would see the structure of it, the bright central bulge where the galactic core lies, the darker rift where dust clouds obscure the light, the gradual brightening toward the center and fading toward the edges. You would see that it is not uniform. It has texture. It has depth. It is, all by itself, one of the most beautiful things a human being can look at. You would see individual stars that you might never have noticed before. Dimmer stars that are normally washed out by lunar glow. Double stars. Star clusters. The fuzzy patches that are nearby galaxies, Andromeda, the Magellanic Clouds in the southern hemisphere, visible to the naked eye as faint smudges of ancient light. Every photon reaching your eye from those stars has been traveling through space for years, decades, centuries, thousands of years. The light from the center of the Milky Way takes about 26,000 years to reach Earth. The light from Andromeda takes about 2.5 million years. When you look at Andromeda with the naked eye, you're seeing light that left the galaxy before Homo sapiens existed. Before the last common ancestor of modern humans and Neanderthals existed. The universe is old, and the sky above us at night is a library of ancient light. Take a slow breath in. Let it out. Your body is heavy and warm. There's nothing you need to do right now. Nothing to figure out. The moon is where it's supposed to be. The tides are doing what they've always done. The axis of the Earth is tilted at 23.4 degrees, and that tilt is stable, and the seasons will keep coming around in their familiar order. All of the things we've talked about tonight, the tidal zones and the estuaries, the coral mass spawning and the grunion running up the beach, the ancient impact that made the moon out of Earth itself, the Apollo boot print still sitting undisturbed in the lunar dust, the water ice waiting in the permanent shadow of polar craters, the 3.8 centimeters per year of outward drift, the billions of years of tidal breaking that slowly lengthened your day to 24 hours, all of it is real. All of it is happening, or has happened, or will happen. And all of it will still be happening while you sleep. The moon does its work whether you're watching or not. The ocean will rise and fall tonight along every coastline on Earth. In some tropical lagoon, perhaps right now, a population of coral is responding to the chemical signals triggered by last night's moonlight, preparing for a spawning event that will happen in a few more days. A sea turtle is navigating by the moonlight reflected off calm water. A dung beetle somewhere is rolling its ball in a straight line, guided by the soft glow of a crescent moon. The world is busy. It's always busy. It never stops. But right now, in this moment, all you have to do is breathe. In and out. Let your eyes stay closed. Let the weight of your body sink a little deeper into whatever you're lying on. The thoughts you had today, the things you're planning for tomorrow, the things you forgot to do, the conversations you're replaying, you don't need any of them right now. They'll be there in the morning. Set them down. Think of the moon, if you want something gentle to hold in your mind. Just that silver white light, steady and ancient. Something that was there before any of your worries existed. Something that will be there long after every worry you've ever had is forgotten. Let that light in your mind get soft. Let it blur a little, the way a light looks when your eyes aren't quite focused on it. Let it become less a specific image and more just a feeling of light. Soft, cool, even light. The tides are rising somewhere right now. Quietly. Without drama. Everything is as it should be. Breathe out. You are safe. You are warm. The moon is right where it's always been. Good night. There is something most people don't realize about how the moon touches even the air we breathe. Not directly, the way the sun heats the atmosphere and drives weather systems. The moon's influence on the atmosphere is subtle. But it is real. Atmospheric tides. Just as the moon pulls on the ocean, it also pulls, very slightly, on the atmosphere. The air has mass. Not much, relative to the ocean, but enough that the moon's gravity creates a small tidal bulge in the atmosphere that travels around the planet as Earth rotates. This atmospheric tide is tiny compared to the oceanic tides. The pressure change is on the order of about 1/100% of normal atmospheric pressure. In practical terms, on any given day, you would never feel it. But over long timescales, in sensitive climate systems, even tiny consistent forces can have measurable effects. Some researchers have found statistical associations between the lunar phase and certain weather phenomena, the timing of rainfall in some regions, the intensity of certain storm systems. Whether these associations reflect real physical mechanisms or are statistical artifacts is still debated. But the fact that researchers look for them at all tells you something about how deeply the moon's influence is threaded through Earth's physical systems. More significantly, the moon affects the amount of ionizing radiation reaching Earth's surface, indirectly, through its effect on space weather. The moon has no magnetic field of its own to deflect charged particles from the sun. But its presence in Earth-Moon space affects the dynamics of the near-Earth environment in subtle ways. On a cosmic scale, none of this amounts to weather in the sense we usually mean. But it contributes to the total physical environment in which life on Earth exists. Here's a simpler connection: cloud seeding, water vapor, and the tidal effect on groundwater. The moon's gravity creates tidal forces in the solid Earth, not just the ocean. The solid Earth flexes, barely, by amounts measured in centimeters, twice daily as the tidal bulge passes. This flexing can affect underground water systems. In sensitive geological settings, tidal forces on groundwater have been measured. They can affect the rate at which water moves through aquifers. They can influence the timing of geyser eruptions. Old Faithful in Yellowstone, for example, has shown sensitivity to tidal stress in the Earth's crust, though the relationship is complex. Even the rocks breathe with the moon. And if the moon were gone, all of those tiny, ancient, interlinked influences, would vanish. The solid Earth would stop flexing twice daily. Geyser systems calibrated to tidal stress would change their timing. Aquifer dynamics would shift. The world is more connected to the moon than almost anyone realizes. There's something almost too fitting about talking about the moon in a context designed to help you sleep. Because the moon and sleep have a real, scientific relationship. For most of human history, the amount of light available at night was directly connected to the phase of the moon. On nights of the full moon, it was bright enough to move around safely, to work, to socialize. On dark nights, near the new moon, there was little to do but rest. The rhythm of lunar phases was, in a very real sense, a rhythm of activity and rest built into the environment itself. A study published in the journal Current Biology found something remarkable. In a group of people studied both in urban settings with artificial light and in indigenous communities with minimal artificial light exposure, there was still a measurable pattern. People fell asleep later and slept for shorter periods in the days leading up to a full moon, and fell asleep earlier and slept longer in the days following the full moon. This pattern held even in people with access to artificial light, though it was more pronounced in those without it. The researchers suggested that this might be a vestigial rhythm, a biological echo of the ancient lunar sleep cycle that natural selection built into human physiology over hundreds of thousands of years of evolution in a world lit at night only by the moon and the stars. Your body, in other words, may still be listening for the moon. The melatonin system, the hormonal mechanism that makes you feel sleepy as darkness falls, may have originally been calibrated not just to the rising and setting of the sun, but to the waxing and waning of the moon. In a pre-electric world, the two light sources that governed human sleep were the sun during the day and the moon at night. Both may have shaped your sleep biology. If the moon disappeared, the long-term consequence, spread across thousands of generations, might include a gradual change in human sleep patterns. Without a lunar light cycle, the nightly light environment would be more uniform from night to night. Only the slow seasonal changes in natural nighttime sky brightness would remain. And the ancient, vestigial biological response to the lunar cycle would, over many generations, become evolutionarily neutral, no longer selected for, and gradually drift away. Humanity would lose a rhythm it has kept since before it was humanity. We talk about the tides as if they are something that happens to the ocean. And of course, they are. But there's a grander way of looking at tidal forces, a perspective that reframes what the moon has actually been doing to Earth all this time. The tides are how the moon and Earth communicate gravitational energy. Every time the tidal bulge forms and the solid Earth rotates underneath it, energy is transferred. Energy flows from Earth's rotation into the moon's orbital momentum, gradually slowing Earth down and gradually speeding the moon up, which, counterintuitively, actually pushes the moon farther away. An object in a higher orbit moves more slowly, so speeding up, in terms of orbital energy, means moving to a higher, more distant orbit. This transfer of energy is relentless. It doesn't rest. It has been happening for 4.5 billion years. The moon is carrying away some of Earth's rotational energy, a tiny fraction at a time, and using it to climb a very, very gentle gravitational slope, moving outward by those 3.8 centimeters per year. There is something poetic about this. The moon, created from Earth's own material, slowly separating from its origin. Moving away. Very, very slowly, but steadily. In the life of the universe, 3.8 centimeters per year is nothing. The universe is roughly 13.8 billion years old. In that time, the moon has drifted outward by a measurable but not enormous amount. It was much closer early on, when the tidal forces were stronger and the energy transfer was faster. It has slowed as the moon moved outward and the tidal forces weakened. There is also something to be said about what tidal forces mean on a cosmic scale. The same forces that drive Earth's oceanic tides, differential gravitational pull across the width of an extended body, are responsible for some of the most dramatic phenomena in the universe. Io, the innermost large moon of Jupiter, is the most volcanically active body in the solar system, not because of radioactive heat, but because of tidal flexing from Jupiter's immense gravity. Jupiter's tidal forces flex Io so violently that the flexing itself generates the heat that powers its volcanoes. Tidal disruption events, when a star wanders too close to a supermassive black hole, produce one of the most energetic phenomena astronomers observe. The black hole's tidal forces shred the star apart, and the infalling material blazes with the brightness of 100 galaxies for a brief time. Tidal forces are gravity in action across a distance. And the moon, humble and familiar, demonstrates this principle every day, twice a day, reliably, for billions of years. Let me take you somewhere very few people have ever been, and far fewer have even thought about. The deep ocean. The ocean floor, in most places, is more than 3 kilometers below the surface. In the deepest trenches, the Mariana Trench, for example, the bottom is nearly 11 kilometers down. At those depths, the pressure is more than 1,000 times the pressure at the surface. It is completely dark. The water is cold, just a few degrees above freezing in most of the deep ocean. And yet it is alive. The deep ocean is home to communities of organisms, bacteria, tube worms, shrimp, fish with bioluminescent lures, gelatinous creatures that drift through the water column, that depend on one fundamental thing, the movement of water from the surface down into the depths, and back up again. This movement is called thermohaline circulation, and it is driven primarily by temperature and salinity differences in the water. But tidal forces also play a role, particularly in the deep ocean, where tidal energy propagates down from the surface and, when it encounters the rough topography of the ocean floor, underwater mountain ranges, ridges, trenches, breaks into turbulence that mixes the water column. This tidal mixing in the deep ocean is not small. It contributes significantly to the global overturning circulation, the slow conveyor belt of ocean water that moves heat from the tropics toward the poles, that brings cold, nutrient-rich deep water up to the surface in upwelling zones, and that takes warm surface water down into the depths in sinking zones. This circulation, which operates on timescales of hundreds to thousands of years, is one of the primary mechanisms by which Earth's climate is regulated. Without lunar tidal forcing, the deep ocean would mix less vigorously. The global overturning circulation would be different. Upwelling zones, where deep, cold, nutrient-rich water rises to the surface and supports some of the most productive fisheries in the world, like the California Current, the Humboldt Current off South America, the Benguela Current off Africa, might be less intense. The productivity of these zones would potentially decrease. Even in the darkest, most remote reaches of the ocean, the moon's gravity has been quietly at work. I want you to picture something. You are standing at the edge of the ocean at night. The water stretches out in front of you, dark and vast, going on for what feels like forever. The horizon is invisible. The darkness of the sky and the darkness of the water blend together somewhere out there, and there is no clear line between them. And then you look up. The moon is full tonight. It hangs low over the water, and its reflection stretches from the horizon all the way to the shore, a long, shimmering ribbon of silver-white light on the surface of the ocean, broken into pieces by the gentle movement of the waves, constantly reshaping itself, never the same from one moment to the next, but always there. Always connected to that round, calm, steady light in the sky. This image, the moon's reflection on the water, is one of the oldest things human eyes have ever seen. Every human who lived near the ocean, in every period of history, on every continent, has seen this exact image. The hunter-gatherers who lived along coastlines 30,000 years ago saw it. The first Polynesian navigators who sailed into the open Pacific saw it. The sailors who crossed the Atlantic for the first time saw it. Every fisherman who ever set out before dawn and came home after dark has seen it. This is what will stay with me from tonight's whole conversation. Not the catastrophe. Not the ecological collapse. Not the wobbling axis and the shrinking tidal zones. The moon's reflection on the water. Something that has been happening. Every night there is a moon and there is an ocean, for 4.5 billion years. And if the moon were gone, that ribbon of light on the water would go dark. And the ocean would keep moving in the dark, and the stars would blaze overhead, and life would adapt and change and continue, because life is remarkably good at continuing. But that particular image, that ancient, silver ribbon, broken and remade by the waves, connecting the sky to the sea, would be gone. And the world would be a little quieter for it. There is something I've always found beautiful about the moon's relationship to the stars. The moon is close. In cosmic terms, practically on top of us. At an average distance of about 384,000 kilometers, it is our nearest neighbor by an enormous margin. The next nearest large body, Venus, at its closest approach, is more than 100 times farther away. The nearest star beyond our sun is about 100 million times farther away than the moon. When you look at the night sky, you're looking at an enormous range of depths. The moon is right there, essentially in our backyard. The planets are a bit farther, next-door neighbors, in cosmic terms. The stars you see with the naked eye are anywhere from a few light-years to a few thousand light-years away. The Andromeda Galaxy is 2.5 million light-years away. And the faint, barely detectable background of the most distant galaxies visible with large telescopes stretches back nearly to the beginning of the universe. All of that depth is visible from right where you're lying. And the moon, close and bright, sits in the foreground of all of it. When the moon moves across the sky throughout the night, rising in the east, arcing overhead, setting in the west, it gradually passes in front of background stars. In astronomical terms, this is called an occultation. The moon moves into the way of a star, and the star disappears behind the moon's limb, silently, instantly, with no warning, and then reappears on the other side after the moon has passed. This is how we know the moon has no significant atmosphere. If it had a thick atmosphere like Venus, the star would dim gradually as it passed through the atmospheric haze before being hidden by the solid body of the moon. Instead, the star disappears instantly. The moon's edge, from the perspective of a star's light, is a sharp, clean line. solid rock. No air. Nothing in between. When you look at the moon, you are looking at the edge of a world. A real, solid, three-dimensional world, hanging in space. Not a painting. Not a reflection. A world. And behind it, in every direction, stretching out to distances that make the nearest stars seem close, the universe goes on and on and on. The moon is ancient, but the universe is so much older. The moon is large, but the universe is incomprehensibly larger. And yet from where you're lying right now, on a Tuesday or a Wednesday or whatever night this is, the moon and the universe coexist in the same window of sky, and you can see both of them just by looking up. That's something. Let's slow down now. Everything we've talked about tonight has moved through time at such different scales. Billions of years. Millions of years. Thousands of years. Centuries. Hours. But right now, we're going to slow down to the only scale that matters to you in this moment. The breath scale. One breath in. Hold it for just a moment. And out. At this pace, the pace of breathing, nothing in the universe is very threatening. At this pace, the slow recession of the moon is imperceptible. The wandering of the axial tilt, measured in fractions of a degree per century, is completely invisible. The inch-by-inch progress of tectonic plates is not something any human will ever feel directly. The gradual brightening of the sun, which over billions of years will eventually boil the ocean, is not something you will experience. All of those forces are real. We talked about all of them tonight. But they operate on timescales so vast that they have no bearing whatsoever on your next breath, or the one after that. On the timescale of a breath, the universe is still. The moon is fixed in the sky. The tides are rising somewhere, slowly and quietly. The stars are turning, very slowly, as Earth rotates, so slowly that you cannot watch them move without looking away for several minutes and then looking back. Everything is slow. Everything is quiet. The day you had is over. Whatever came with it, the things that went well and the things that didn't, the conversations that felt good and the ones that didn't, the tasks completed and the ones left for tomorrow, all of that is over. It exists now only as memory, and memories are quiet. They don't press. They don't demand anything of you. What demands something of you right now is only sleep. And sleep is easy. Sleep doesn't ask you to do anything. It only asks you to stop. To let the thinking slow. To let the images behind your eyes soften. To let the sound of my voice become something you're not really tracking anymore, just a texture of sound, like rain on a roof, present but not requiring your full attention. Your body knows how to do this. It has done it every night of your life. Let it do what it knows how to do. Let your thoughts drift. If you were standing outside right now, and the sky was clear, and you looked up at the moon, whatever phase it's in tonight, I want you to hold that image in your mind for just a moment. Not the scientific version of the moon we've been talking about tonight. Not the gravitational stabilizer, not the tidal engine, not the geological record of 4 billion years of impacts. Just the moon the way you've always seen it. Maybe it's full. Round and complete, brighter than you'd expect, washing out the dimmer stars and painting the landscape in that cool, flat, silvery light that makes everything look like an old photograph. Maybe it's a half moon. One side lit, one side dark. The line between them, the terminator, sharp and curved, running through craters and plains, the shadows inside the craters long and dramatic along that line. Maybe it's a thin crescent, curved like a smile or a cradle, close to the horizon just after sunset, already heading toward the dark. The rest of the lunar disk just barely visible as a dim, ghost-gray circle lit by sunlight reflecting off the Earth, what astronomers call Earthshine, or the old moon in the new moon's arms. Whatever shape it is tonight, it is the same moon. The same 4-billion-year-old world. The same piece of Earth, remade by impact and gravity and time. And it will be there tomorrow night. And the night after that. And for as long as you and I are alive to look up at it, and for many generations beyond that. This is not something to take for granted. Most planets don't have a moon like this. Most moons didn't form the way ours did. The combination of factors that gave Earth this particular companion, the right size, the right distance, the right composition, is, as far as we know, unusual. We are fortunate. And tonight, knowing even a fraction of what that moon has done for this planet, for the ocean, for the ecosystems, for the evolution of life, for the length of your day, for the stability of your seasons, for the countless generations of human beings who navigated and farmed and sailed and dreamed by its light, knowing all of that makes it something more than just beautiful. It makes it a presence. A 4.5-billion-year-old presence. Quiet, steady, faithful. Right where it's always been. Now close your eyes. Let the image of that light stay with you, softening, fading gently, becoming less a picture and more a feeling. A feeling of light. Cool and silver and ancient and close. You don't have to hold on to it. Let it drift if it wants to drift. Let it carry you somewhere quiet. You are safe. The moon is out there. And you can sleep now. Total script length, 100,000 characters. Before we fully let the night take over, I want to walk you through something on the grandest possible timescale. Not billions of years, we've done that. Just millions. The kind of timescale where you can actually imagine the landscapes, even though no human was there to see them. Imagine Earth about 300 million years ago. A completely different world. The continents were arranged differently. In fact, most of the world's land masses were in the process of colliding, slowly, to form the supercontinent Pangaea. The coal swamps that we now mine for fuel were alive and growing, vast forests of giant tree ferns and club mosses stretching across the equatorial regions, so productive that the oxygen they released raised atmospheric oxygen levels to perhaps 35%, compared to today's 21%. Giant insects buzzed and crawled through these swamps, dragonflies with wingspans of 2 feet or more, millipedes 3 feet long. And the moon was there. Closer than today, the tidal forces were somewhat stronger. The ocean tide swept in and out across the shallow coastal seas that bordered Pangaea. The intertidal zones were rich and productive, as they are today, or richer. The axis of Earth was stable, held in place by the moon's gravitational steadiness. The seasons came and went. The ocean circulated. Organic matter was buried in vast quantities, the material that would eventually, over hundreds of millions of years of heat and pressure, become the coal and oil that modern civilization has been built on. The moon did not deposit that fossil carbon, but the stable climate that allowed those vast, productive swamps to exist and accumulate over such long timescales, that stability was partly the moon's gift. Now go back farther. 500 million years ago. The Cambrian explosion, the remarkable evolutionary event during which most of the major animal body plans appeared in the fossil record in a relatively short span of geological time, perhaps tens of millions of years. Before the Cambrian, complex multicellular animal life was relatively rare. After it, the oceans teemed with creatures with eyes and shells and limbs and nervous systems. What triggered the Cambrian explosion is still debated among evolutionary biologists. But whatever triggered it played out in ocean ecosystems shaped by Cambrian tides, which in turn were driven by the Moon, sitting in its orbit somewhat closer than today, pulling the water with somewhat more force. The intertidal zones of the Cambrian were wide and productive. The shallow coastal seas were rich in the nutrients mixed by tidal currents. Life had a stage to play on, shaped in part by the tidal environment that the Moon provided. And farther back still, 700 million years ago, 800 million years ago, a time that geologists call the Cryogenian, because the evidence suggests that Earth underwent at least 2 episodes of extreme glaciation during this period, during which ice may have extended from the poles all the way to the equator. Snowball Earth. The ocean, largely frozen over. Life, clinging on in the liquid water that remained beneath the ice, or near volcanic hot springs, or in isolated pockets of open ocean. The Moon was there for Snowball Earth. It kept pulling the tides, even under the ice. Even in those extreme conditions, the gravitational partnership between Earth and Moon continued. The tidal forces continued to slow Earth's rotation, to stabilize its axis. And when Earth emerged from those glaciations, rapidly, geologically speaking, due to the buildup of volcanic carbon dioxide in the atmosphere, the Moon was there, stabilizing the axis as the climate restabilized. Ready for the long, slow, gradual buildup of complex life that would eventually produce everything you know. For the history of astronomy, the Moon has been the first and most important laboratory. Astronomers and philosophers of the ancient world could observe the Moon with naked eyes and reason carefully about what they saw. In the 3rd century BCE, a Greek astronomer named Aristarchus of Samos used the geometry of the Moon during a lunar eclipse to estimate the distance to the Moon. He knew that during a lunar eclipse, the Moon passes through Earth's shadow. By measuring the size of Earth's shadow on the Moon and comparing it to the known size of the Moon, he could work out a ratio. His estimate of the Moon's distance was remarkably good for a calculation done with no instruments beyond careful observation and geometry. Another Greek astronomer, Eratosthenes of Cyrene, who became famous for his remarkably accurate estimate of Earth's circumference, built on this work to reason about the sizes and distances of celestial bodies. These ancient scientists, using only what they could see with their eyes and what they could calculate with their minds, worked out the approximate scale of the Earth-Moon system within a reasonable margin. When Galileo pointed the first telescope at the Moon in 1609, what he saw overturned centuries of belief. The Moon, which Aristotelian philosophy held to be a perfect, smooth sphere, part of the perfect celestial realm beyond the imperfect Earth, was anything but. Galileo saw mountains. He saw valleys. He saw craters and plains. He saw, in short, a world. A place with geography, with topography, with the marks of a violent history written in its surface. The Moon was not a divine light in the sky. It was another piece of the cosmos, subject to the same physical laws as Earth. This was a revolutionary realization. And it began with looking closely at the Moon. Newton's theory of universal gravitation, one of the most important intellectual achievements in the history of science, was validated in part by the Moon. Newton worked out that the force of gravity between two bodies depends on their masses and on the inverse square of the distance between them. If this law was correct, then the same force that made an apple fall from a tree should, diminished by the square of the distance, be exactly the right strength to keep the moon in its orbit. And it was. The moon's orbital period and orbital distance, plugged into Newton's equations, gave back the same gravitational constant that explained the fall of objects on Earth. The moon told Newton that gravity is universal. Not just a local Earth phenomenon, but a force that operates the same way at every distance, on every scale, across the entire universe. This is what science does. It uses the things close at hand to understand the things far away. And the moon, so close, so well observed, has been one of the most productive laboratories in the entire history of human scientific inquiry. Have you ever actually watched the moon rise? Not noticed it in the sky, where it was already high above the horizon, but actually stood somewhere and watched it come up, the way you might watch the sun set. The moon rises slowly. Slower than you'd think, but fast enough that if you stay very still and watch, you can see it moving. It comes up over the horizon, or over a ridgeline, or over a rooftop, depending on where you are, orange or amber when it's low, the way the sun is orange at the horizon. This is because when the moon is low, you're looking at it through a much thicker slice of Earth's atmosphere than when it's overhead, and the atmosphere scatters the shorter blue wavelengths of light and lets the longer red and orange wavelengths through. The same physics that makes sunsets orange makes moonrises orange. A full moon rising is one of the genuinely striking visual experiences available to anyone, anywhere, at no cost. It's enormous looking at the horizon, though this is actually an optical illusion called the moon illusion, where the brain perceives the moon as larger when it's near horizon-level objects like trees and buildings, compared to when it's isolated in the empty sky overhead. The actual angular size of the moon doesn't change, but it looks bigger. And in that low, orange light, immense, clearing the horizon slowly, it looks close. It looks like you could reach out and touch it. As it climbs, it shrinks, or rather, it looks smaller, because the illusion fades as it rises above the clutter of the horizon. And it shifts from orange to yellow to white, as the thickness of atmosphere you're looking through decreases. By the time it's high overhead, on a clear night, it is brilliant white and steady, and the landscape below it is silver. On a full moon night, if you are somewhere without artificial light, the change in the world when the moon rises is visceral. Before moonrise, if you're out of the city, the darkness is deep. Stars are visible. The Milky Way might be bright. And then the moon clears the horizon, and the world changes. The ground lights up. Shadows appear. Colors are muted. Human color vision works poorly in dim light, but shapes are clear. Rocks, trees, water, all of it rendered in silver and shadow by the rising moon. It is very, very easy to understand why the moon became sacred to so many people in so many cultures. It changes the world simply by appearing. Let me be quiet with you for a little while. You don't need more information tonight. You've traveled far enough, from the intertidal zone to the deep ocean, from the ancient impact that made the moon to the footprints still sitting in the lunar dust, from the wandering axial tilt of a moonless Earth to the soft silver light on the surface of the water. You've done a lot of thinking tonight, even if it felt like just listening. Your mind has been busy. Gently busy, not the anxious kind of busy, but the curious kind. The kind of busy that leaves you feeling full. Satisfied. Like after a long walk in fresh air. And now the walk is over. You're inside. You're warm. The world outside is doing what it does. The moon is moving through the sky, the tides are quietly rising and falling somewhere. A coral polyp somewhere is responding to the faintest change in light levels that no human eye could detect. A sea turtle is swimming through dark water following the glow of the sky. And all of it is happening without your help. Without your attention. Without you needing to think about it at all. The world can manage without your attention for a while. It's managed without it every night of your life, and every night before you were born, and it will manage long after this particular night is over. All you have to do is breathe. And rest. Let the weight of everything you've been thinking about settle down into stillness. Let the images, the tidal pools, the moon's reflection on the ocean, the orange moonrise, the blizzard of coral spawning in the warm Pacific night, let them slow and soften. Let them become less distinct, less sharp, less demanding. You are not responsible for any of it tonight. Not the moon, not the tides, not the ecosystems that depend on them, not the axial tilt of the planet, not the ancient impact that created the world you live on. All of it will take care of itself. Your only job right now is to let your body do what it knows how to do. Breathe in. Breathe out. The moon is out there. Ancient, patient, steady. 384,000 kilometers away, traveling the same orbit it has traveled for 4.5 billion years, pulling gently on the ocean, keeping the axis of your world in place, reflecting sunlight down onto sleeping cities and sleeping oceans and sleeping forests. You don't have to watch it. You don't have to understand it. It doesn't need anything from you tonight. Just let it be there, in the background of whatever you're imagining as you fall asleep. A quiet presence. A silver light on the far side of your eyelids. And let yourself drift. You've earned it. Good night. Sleep well. The goal throughout has been to keep the listener's mind gently occupied, curious but not anxious, engaged but not alert. The topics move from immediate to vast, from personal to cosmic, from concrete to abstract, in a way that mirrors the natural movement of a mind drifting towards sleep. Concrete early, then images, then pure sensation, then quiet,